Okay, so welcome everyone for the first Boston masterclass of 2019. So we are planning a couple of workshops, one in the Boston area, one in New York, DC, San Francisco, and Chicago. And this is going to be the launch of the certificate program we are offering in the context of data science, machine learning, AI, and optimization. And today's masterclass is going to give you an overview on 4 topics we have picked to kind of introduce you to some of the concepts in that area, but also give you a perspective on some of the innovations which are happening in that space so that you can consider enrolling for a full certificate program if that's of interest. Okay. So for people who don't know, how are you?
Good. I was just trying to see if I could help you with the tech issues.
I think we should be set.
Oh, you're all set?
Yeah,
oh, perfect.
Okay. I think the video is going to be. So my name is Sri Krishnamurthy, and I run this company, QuantUniversity, and we are an analytics advisory. How many of you know QuantUniversity? Well, everyone in the room should know. So for people who are online, we are an analytics advisory based out of Boston. We started out primarily in the consulting space, and we have been offering a lot of workshops, primarily in data science, machine learning, with applications in the financial services and energy industry. Most of my career has been in the financial services space, so I bring in a lot of lessons learned in the context of data sets which we use in the financial services space and how the newer technologies are kind of impacting those applications in the financial services space. So we have a couple of certificate programs already in place. One is a fintech certificate program, another one is an analytics certificate program. We primarily offer that for companies, and we go into companies and we certify those people after a bunch of training programs. And today's masterclass is going to be a preview of the new certificate program we're putting together, primarily in the context of optimization, forecasting, data science, and artificial intelligence. So as most of you know, I teach at Northeastern University. We have many of our students in here. And I also have been an adjunct at Babson College, and it always energizes me to come back to Babson, and I would like to acknowledge the support of Babson College for hosting us for this workshop. And I've also been active in the context of trying to bring in frontier technologies into financial services. So my interests include bringing in like the newer and the untested technologies to see if there's real value in those applications in the financial services space. Now, as you all know, financial services is different. It's not, when stocks move, it's not like a physical process wherein you have a particular goal you want to achieve, and you want to basically kind of get to that particular goal. You have to model it in such a way so that you are at least capturing some of the nuances of behaviors of these assets, and see if you can potentially use it in the context of either forecasting or in optimization. Now, with machine learning and artificial intelligence kind of coming in full vogue, and we are seeing a lot of applications in space, one area wherein there's a lot of confusion is how do we adopt these technologies in the financial services world? And in order to facilitate that, what we did was we looked at the key challenges in building data science applications. And the first session you're going to hear from me today is this framework, as we call, as the 10 steps of data science. So what are the key ideas and what are the key things you need to consider when you're building out data science applications in enterprises? And I'm going to show you a case study using the Q Sandbox, which is our platform for building out data science applications, on how we have facilitated those 10 steps and how you can deploy, start from inception and go to production of data science applications. So it's kind of a mini case study, and obviously the full workshop will give you a full-fledged case study and the elaborate steps, but I would like to start by at least orienting you on that framework. The second talk, Dr. Vicentini, who is on the way, so he primarily focuses on time series analysis and econometrics. And he has had a career in consulting at an economic consulting company, and primarily his goal was to make sure that many of the challenges his customers was having, and how do you address it with time series and econometrics methods. And Gustavo, a good friend of mine, he's also been teaching at college and teaches how, but at Northeastern, he's primarily focused on teaching econometrics and time series methodologies, and he's been helping QuantUniversity in structuring some of the programs in the context of econometrics and time series analysis. The focus of this session is to kind of go to the nitty-gritties of what would it take to build out time series applications, rather than just kind of give you, just some applications. And the reason we thought this was interesting is when people study data science, a lot of people just think that we can learn from data and we can build out models. But there's a lot of rigor involved in building out time series and econometrics-based applications. And if you don't really understand the nature of these time series data sets, it becomes hard to just model out these problems. So in today's session, Gustavo is going to talk primarily on how do you structure these problems. And in the future, when we do a full workshop, we're going to talk about further innovations in the context of using LSTMs and neural networks and further technologies. And the third session would be by Anish. Anish is an expert in optimization. And when we've been talking about putting together a workshop on optimization, we've been brainstorming on what are the key ideas we're going to bring into this workshop. So as most of you know, Anish is a very creative guy. So he's been playing guitar the last, the mental guitar on optimization, if you will. And he's put together a very interesting presentation. It's fresh off the press, and I'm very eager. I've not heard that or seen that presentation yet. So I'd love to hear his thoughts on where optimization is going. And if time permits, we're also going to show you some demos on some of the tooling which is out there in the context of optimization. How do you structure these optimization problems? There's a lot of innovation in the open source space on building out optimization problems. And frankly, the rigor of time series analysis and optimization is getting lost with the buzz of machine learning and data science, because there's a lot of interest in kind of bringing out these solutions to the market, but people are kind of missing out on the amount of rigor that is involved in modeling out these problems. So we want to kind of revisit the structuring of these problems and what does it mean to put together these problems to address some of the challenges of optimization. And in the last session, I'm going to try and connect all these concepts with a full-fledged case study in the context of artificial intelligence and machine learning. Now, most of the times when you build out algorithms, you had to think about various thought processes on, how do you optimize this algorithm? How do you tune various parameters? Do you manually go and select different algorithms, or do you figure out different approaches of choosing these algorithms? So here I'm going to talk about one major innovation which is happening in the space, and that's AutoML. And a lot of companies are building out products to automatically choose different algorithms, and I'm going to focus mostly on how do you structure an optimization and a machine learning problem, and then look at AutoML-based techniques for figuring out the best possible problem. And we'll have a case study for you to illustrate some. So the first thing I want to kind of talk about in the context of data science is, well, we have had an influx of various innovations the last 10 to 15 years. The way we have seen data growing has significantly increased. You are no longer just collecting data on a daily basis. Every couple of seconds, you're getting new bits of information, either as news flashes or updates in terms of your applications. The velocity at which the data is coming in has significantly increased. In addition to that, the whole big data phenomenon, which people keep talking about. So this has resulted in a huge wave of newer products and technologies, which has helped you to kind of collect, process, analyze, store, and also transmit various bits of information. So with all those innovations out there, people have to think about how can we leverage these technologies, because the technology of the 2000s or the 1990s is not going to be easy to just migrate and there's a lot of these solutions. You have to come up with a whole paradigm shift on how do you actually use these applications when you're building out data science applications. Secondly, the algorithmic frameworks which people have been working with. So this has gone through a major revolution, especially if you look at the frameworks which are posted out there. Only one of them is a commercial product. The rest of them are all open source projects. So we have seen a lot of innovation in the Apache ecosystem. And because of this open innovation, you are seeing various frameworks by which you actually work with technologies which, within a couple of seconds, you'll have access to the whole stack. You can just download it and start using it in a few seconds. So that's another major innovation in the context of algorithmic frameworks. But also, there are innovations which people thought would never happen, and in deep learning is bringing out newer innovations, which is changing the way people think about processing data. Most of the statisticians and operations research specialists were focusing on models, and deep learning basically changed the paradigm completely. And you're focusing on the nature of the data you're going to be looking at, and thinking about choosing different architectures to be able to map these data sets to different kinds of models. And here, the fascinating thing is every company you look at, CNTK, for example, is Microsoft product. MXNet is heavily influenced and supported by Amazon. TensorFlow is heavily supported by Google. So you are seeing a lot of newer frameworks which are going to be helping you design and structure and deploy various kinds of algorithms. So these are, we talked about the data, we talked about the algorithms, but if you have data, if you have algorithms and you don't have hardware, how can you process it? And that's where we are seeing a lot of innovations in the context of hardware. So we are seeing companies like NVIDIA putting together infrastructure which will help you run calculations which would potentially take days, and those would take just a few hours or sometimes even a few minutes with the way you can potentially scale these technologies. And now we are talking about not just using one GPU, we are using a family of GPUs. We can connect multiple GPUs, and then you can potentially deploy it on the cloud and then run really humongous calculations. Sometimes these calculations would take many, many days. We are seeing those calculations take place in a couple of milliseconds. So with all this said, the motivation I want to have for you is, when people talk about data science applications, you are not just taking a particular data set which comes in a CSV file or some Kaggle data set and then figure out which model is the best particular model. So you have to think about comprehensively all these aspects of what kind of data am I working with? Is it a high velocity data set? Is it a voluminous data set? Are there multiple dimensions in this data set? What kind of hardware infrastructure should I be looking at? What kind of algorithmic framework should I be looking at? So all these are important questions you need to ask. And many times we kind of miss that perspective, especially in financial companies. And we think about a quant or a data scientist has to work on a particular problem. And let's just focus on that particular problem and get the best solution out there. And let someone else take the next step of deploying these solutions and then making this operational. So that's why I want to kind of set you up with a framework which will help you kind of think about the various facets of data science problems and see how you can model those problems with all of these perspectives in mind. Now, when people talk about typical data science workflows, this is what you typically see. You see data cleansing, you see feature engineering, training, testing, model building, model selection, model deployment. Many a times you see it as a sequential workflow. But the reality is you will never be able to run everything in one step. These are iterative processes, and many a times you have to go back and forth to make sure that the data gets processed in a particular way. And if it's not operational, you have to kind of go back and revisit the approach and then kind of work with it from scratch again. So what I would like to talk about today is not just about algorithms. Many times when we talk about data science, people just focus on the algorithm. And there are a lot of cheat sheets, like for example, this is a Microsoft algorithmic flowchart, which talks about how do you choose an algorithm for a particular problem. Are you looking at an anomaly detection or a fraud detection kind of problem? Are you looking at a multi-class classification problem? Are you looking at a regression problem? Are you looking at a recommendation system kind of problem? So depending on the problem you have at hand, depending on the data you're going to be working with, you have to choose a particular problem. So there are a lot of frameworks which will help you kind of choose the particular algorithm. But let's start focusing on, how do you structure and think about data science problems in the first place, right? So this methodology, I've taught this methodology in the classroom too. So we're kind of going through stage by stage in the class I'm teaching at Northeastern University about framing a problem and designing problems, things like that. But I want to give you like the big picture on what does it take to build a data science application. The first thing you need to talk about when you talk about designing data science solutions is not about the data. It's about the business problem you're trying to solve. So if you do not have a perspective on why you're investing all this infrastructure to solve a particular problem, if you do not have that perspective, it's absolutely useless to just take all this data and then kind of process it. So the first thing you need to do is articulate what the business problem is. Am I trying to reduce cost, or am I trying to increase sales, or am I trying to get a particular forecast at a particular point in time? So those statements will help you kind of define the data science problem. The second thing is very important. Those are like the data-related questions. And this would be, things like what kind of data would you need? Where would you get this data? And do you even have the data? If you do not have the data, where do you have to go and get those data sources? And even if you have the data, if you have stored the data, is the right kinds of data sets. So many a times you think that you have the data, but data science problems require data in a very structured way to learn from those data sets. So if you do not have those data sets, what do you have to do in order to design those data sets? And the other big question is, will you continue to have data? Because many times you may have a snapshot of the data and you think you'll build a model from it. But on a regular basis, are you going to be getting the data? And if not, what data sources you have to think about sourcing in order to get those data sets? The third aspect is the data acquisition and the data prep strategy. Now here, the biggest question is, how do you actually get the data? Many times you may have to scrape the data from multiple websites. It may not be easy to just connect to a particular data set and get it. If you are building a sentiment analysis engine, which will show you about case study for a little bit, you may have to scrape Twitter or subscribe to a Twitter data feed. You may have to think about scraping data sets from PDF files or from HTML files. So you may have to think about those strategies and how do I, in a concrete, in a structured way, have a process by which I can get those data sets and then start working with those data sets. The second thing is data has to be governed. It's not that you just got the data and you put it in a database and you forget it. You had to think about versioning these data sets. You had to think about which data set was used to build a particular model. And it means that you have to have a way in which you can snapshot the data and then figure out like which model was attributed to which particular data set. Because your data keeps growing. As you get new information, your data sets keep growing. So you may have to let go of older information which potentially is not influencing your model anymore. And you may have to factor in newer information with a higher weight. So all those aspects have to be thought about when you're defining your data preparation and data acquisition strategies. The fourth step is evaluating and exploring your data to figure out whether it's in the right format. Many a times, people jump into the modeling mode once they acquire the data. And this is a very bad practice. Because if you do not really understand the nature of the data you have, you may just be tuning your algorithms for data sets which may not be complete. Maybe the data does not have all the right values. Maybe it has spurious values in it. It may have missing data sets. So if you want to figure out a way in which you can clean up the data set or to focus on the data sets which may be of interest, you have to think about exploring and understanding your data sets well. So it involves a lot of visualization, summarization techniques, and many a times there is an exploration mode data scientists will have to go through to ensure that they have a clear idea on what kinds of data sets they're working with. And the fifth step is defining the goal. So we have a business problem. We know what data sets we're going to be working with. We have explored and we've figured out what we're going to be doing with the data. And now we have to define, before even selecting a particular algorithm, what am I going to be doing with this data? Right? Am I going to be summarizing it? Because we have a lot of data and I would like to get certain insights. So I want to be able to summarize this data set. Or it could be a fact-finding mission. Maybe you're looking at your past sales data, or you're looking at data sets you've collected in the past, and you're figuring out, can I attribute certain spikes to certain market events? Can I attribute certain spikes to something which has happened to a particular portfolio company which had certain market events? So in order to figure out what has happened in the past, you may have to go through a fact-finding mission. So that could be your potential goal. Your goal could be just understanding relationships. You have a hunch that a particular economy has a correlation on certain natural resources, maybe oil or whatever it is. So can you build and formalize those relationships? So can we go back and figure out those relationships and understand those relationships? That could be a goal. It could be prediction. So here's the key. All data science problems are not prediction problems. So when you talk about data science, it's not always the goal that you're building out an algorithm which is expected to forecast or predict something in the future, right? Many Kaggle challenges kind of focus heavily on the prediction aspect. They just basically give you, here's my training data set, here's my testing data set, go build a model which maps your X to Y. So that's not always a data science problem. Prediction is one of the data science challenges which are out there, but there are so many other problems which could potentially be looked at in the context of data science. So once you have defined your goal, then comes choosing the algorithm frameworks which you could potentially use. I want to emphasize that you're still shortlisting an algorithm and you're not choosing an algorithm yet. Many a times data scientists make a mistake of saying, I'm going to use a neural network framework for this particular problem, or I'm going to use a regression framework for this particular problem. We still don't know yet. So you have to think about the family of algorithms to potentially explore before you can even say or choose a particular algorithm. So that becomes key, because once you have shortlisted your algorithm, now even before you can start trying out these algorithms, you have to start figuring out the constraints. So I'm kind of introducing some of the keywords potentially Anish is going to talk about too, in the context of constraints, in the context of optimization and things like that. But these could be constraints which you will have in the context of any business. And there, the constraints could be beyond structuring of technical problems. So you have to think about what potential business constraints we may have. Maybe we cannot deploy stuff on the cloud, which means that I can't use any of the public cloud services that are out there. Maybe our data acquisition strategy is such that we will only be getting certain snapshots, on a daily basis. So we may have to structure those approaches so that those daily updates could be factored in our modeling process. And we may also have to think about aspects as well. What's the value in taking a particular approach? And even if there is value, what's the cost of taking that particular approach? All these are important questions, and that's where it's not purely a technical decision to choose the methodology. You have to think about the business constraints and the business aspects of what does it mean to build out a data science solution. And then the goal is always about outcomes, what do you intend to achieve when you build out this whole process, and how do we actually get there? Now, the 8th step is the criteria. Even before you start testing out these algorithms, you have to build out a criteria on how do you choose a particular model, right? Certain things you'll have to think about. Is this process replicable? So if I build out a whole thing and I deploy it in production, can I replicate the process on an ongoing basis? What performance metrics are we going to be choosing? Am I going to be minimizing the mean absolute error? Should I be looking at a particular metric for classification versus regression? Should I be looking at one class versus the other class? So all these are important questions you'll have to ask. And then figuring out whether it's going to generate enough business value for you to keep this process involved. Now, data science, as you know, is learning from data, right? So if the process of this whole acquisition, building out a model, generating the nuggets, does not generate enough information for you to make some quality decisions, then the whole process is waste, right? So articulating and quantifying those outcomes and the business value is going to be extremely important. Okay, and then you had to start figuring out, what algorithms and how do you tune your algorithms? Because you've now shortlisted a bunch of algorithms. You've just established a performance criteria saying that I'm going to choose an algorithm or a model based on a particular metric. Now comes, how do you actually get to the best possible result with the constraints you have in mind, with the choices you have made, and with the other aspects of the modeling framework you've already done. Right? So here, you may have to think about some of the aspects we're going to talk about in the fourth session, things like hyperparameter tuning, which are the choices the data scientists will have to make, figuring out how many trials am I going to be running, what's my stopping point for a particular algorithm, what's the bias-variance tradeoff. In case I'm handling imbalanced class problems, how do I go about handling those kinds of problems? Should I be, should I just close the door? So should we be looking at multiple algorithms? Instead of just using one algorithm and choosing one algorithm at a time, can we combine multiple algorithms and use those algorithms for prediction? And then we'll talk a little bit about AutoML in the final session. Can we automatically choose algorithms based on certain frameworks? Okay. So this is where, based on all the structuring of the problem, you will be able to come up with the best possible replicable process and algorithm you can potentially deploy. And then finally, you had to think about, how do I make this whole process accessible to business decision makers? Now, there's a lot of confusion in the marketplace. Financial professionals, are thinking that, well, everybody has to go about learning Python and start coding, because that's the way you can actually use data science. Right? That's always not the case. You have some subject matter experts, some programming experts, some statisticians, some data scientists who could potentially build out these models. But ultimately, the decision makers need to have the tools so that they can actually use those tools for decision making. Right? So the question becomes, how do you make these tools and analysis available to the end users? Right? So here you may have to think about, well, I've done one problem. I may have to run hundreds of problems. So can I build all the infrastructure on site, or should I be deploying it on the cloud? What are the frequency of data and model updates? Obviously, a decision maker is not going to be making those decisions on, okay, I need to refresh my data and run my model again, right? Because that has to be programmatically built into this process. And then comes the question of governance. Who's going to be managing all these processes? Who's responsible to manage all this infrastructure? And that is very important, because if one decision maker has kind of put together the whole process, and the person has to take a vacation, so who is going to be managing the process? If it's not properly defined, then you may see disasters happen. Right? And then also some of the key ideas which has permeated in the industry, like how do you think about speed, scalability, availability, disaster recovery, rolling back a particular process. and also pulling the plug. If the model isn't working and it's making decisions or faulty decisions, how do you pull the plug and kind of cut the losses? So all those aspects have to be thought about when you're building out and deploying these solutions out there. So my goal to kind of relay these 10 steps are like the 10 things you have to think about in the context of data science applications goes beyond just structuring a problem. But I also want to emphasize that it's not just sufficient to think about data science as a technical process wherein you are trying to achieve something. So many people think of it as a technical project like building a website or setting up a new database. It's just another technical problem. It's a project-based thing wherein we are going to do certain things and we have an end result and we'll move on from there. It's not always the case because data science is a complete paradigm shift on how you're going to be changing your decision making, and it's a new asset you're bringing in the context of decision making. And you have to think about this is a bonus step. I couldn't fit it into the 10 steps. Think about like how do you retune your model? What things need to be monitored? How do you factor in delay or decays in the model? If the model starts degrading in performance, how do you actually go about it? And what aspects of data augmentation do you need to think about? Because as you know, the data sources are constantly increasing and alternative data vendors are giving you newer insights and newer data sets every day. And in case you're trying out new data sets, how do you actually factor that in? How do you think about bringing new data sets into your business process? And then lastly, everyone wants to try out newer innovations. As I said before, neural networks and some of the newer technologies, the innovation is happening on a daily basis. Many of these frameworks are constantly evolving, and you have to have that process in mind so that you can factor these newer innovations and bring that into your core practices. You can't just have like a static workflow and say, you're kind of done. So you have to have a robust monitoring process so that you can test your efficacy of the solution and be open to constant change and constant innovation. Okay, I'll stop here for a second before we move on to case studies. So I want to see if there are any questions. Yes, please.
The data flow always sort of seems to start. Where's the data come from?
Right. Depends on what data set you're looking for, right? Because let's pick an example. If you're
Mutual funds.
Mutual funds, right? So what areas of interest do you have in the context of mutual funds? So the mutual fund is made up of, let's say, I don't know, 30 stocks. Right? So you're interested in kind of monitoring each one of these stocks. Right? Now, how do you collect information about these stocks? If you're a portfolio manager and you're trying to figure out what my constituents of this fund should be, so you have a watch list. You're watching some potential stocks you would potentially want to bring into your workflow, right? You're also looking at things like, well, they could be market events. There are earnings calls. Should I keep this stock in my portfolio or should I be letting it go? Right? All those aspects will involve you to make decisions based on the information you are getting. You have certain information and you have basically made your decisions based on the information you have had till now. Now you're getting newer information and you need to make decisions now. Right? So where do you get the data? Right? You could potentially get feeds, data feeds, which will give you that information, but there may be a delay. You could potentially get like Twitter feeds. Bloomberg has a Twitter feed, and you could potentially have a feed for all the stocks you are potentially addressing. So that could be an alternative feed. And you could get like regular factor feeds, like companies like Northfield and others could potentially be giving you factors on a regular basis. And then you can figure out the risk exposures based on various sectors and things like that. You could potentially be getting those. So those could be our data sources, and you may be collecting it in different ways. For example, I gave an assignment to some of my students this semester to figure out like hiring trends in various companies. And if you're trying to project where a company is going, the best way to look for it is what kind of people are they hiring? What kind of projects are they having? Right? So you may be interested in figuring out like what kind of people are they hiring? Where are the openings out there for various companies? So that could be a piece of information you may want to gather. Right? So those are some of the, depending on the information that's where you have to start framing the problem. What am I trying to solve and what problem I'm trying to address? Any other questions?
Professor, you discussed about the model management in your one slide. So how do you know that you have to, retune your model, or once you have deployed, what are the parameters or what is the strategy to think about, oh, I need to, retrain or retune the model. So what are strategies to figure out, okay, this is the time now, I need to retrain them or retune them?
Yeah, so retuning may not always be possible. So if you're trying to do summarizations, you just basically choose a particular set of metrics and you're tuning, or you're basically summarizing those metrics. But if you have a prediction problem, now you have certain predictions in mind, and you have forecasted certain things. And Gustavo just came in, he's going to talk a little bit about forecasting. So you made certain forecasts. Now, it's not just sufficient that you made certain forecasts and you took a decision and moved on, because those forecasts may or may not have been realized. Right? So you may have to start defining a metric on when do you want to retune your model. For example, so if I'm making forecasts for weather, right? So every day, I'm a weather station, I'm making forecasts for weather. And I'm getting wrong every other day, which means there's something wrong with my forecasting model, which means that I have to retune my model, right? If I'm making forecasts on certain earnings numbers, or if I'm making certain forecasts on economic parameters, if you're not good, getting it right, even to acknowledge that you're not getting it right, and then figuring out a way in which you can correct it, has to be systematically done. Right? So that's where you have to build out a monitoring process to figure out, well, I made certain forecasts. You had to collect metrics on how good were my forecasts and what should happen in order to change those. So that should be factored in your whole process. It's not just about building a model and deploying it.
Thank you.
Any other questions before we move to case study? Okay, so the case study I want to illustrate is a case study we have structured from scratch to do sentiment analysis. And I'll kind of talk a little bit about the business problem and walk you through how we have structured the solution for this particular problem. So most of you know that the drivers in the market are changing, right? And I presented the slide in multiple meetups. Now, a couple of probably close to 6 months ago now, Elon Musk sent out a tweet, and this was 9:48 in the morning, and he basically sent out a tweet saying he's going to take Tesla private, right? And it was 12:48 East Coast time, right? And Bloomberg actually posted it was kind of an advertisement for their event-driven feed, and they posted a LinkedIn post basically saying that at 12:48, and this is kind of the timestamp when the original tweet was actually acknowledged on the event feeds, and at 12:48 was when the tweet actually hit the Twitter feed, and the news flash was already there on Bloomberg feeds within half a second, right? And this kind of talks about the market impact. Within a few seconds, the market impact was already seen. So because you have algos doing most of these trades, the information was immediately processed and was immediately factored in, right? So if you are a fundamental asset manager and you're kind of not tracking some of these alternative feeds, many times you may lose out on that information. You may kind of, get and process the information at a later point in time, right? So to emphasize, well, there was also some lawsuits, obviously, so you kind of follow the story from there on. So the key idea is, sentiments drives markets. So how do you factor this newer information source, right? So that is one way of thinking about the problem. You have to factor in your information sources. Another challenge which a lot of companies are having is, they are basically thinking about alternative ways of processing information. And that's the reason why a lot of companies are beefing up their AI and machine learning units. And what are they actually doing when they hire all these data scientists, right? So we did a workshop in New York last year on deep learning. And we had 6 data scientists from JP Morgan come down. And each one of them had a PhD. And their mandate was they had terabytes of PDF files about various companies. And they basically wanted to process all that information and provide a searchable way in which they could go and basically collect information from all these news and other PDF files, research files that are already collected. So they're looking for natural language processing techniques to be able to process and filter and summarize all this information. So there's a lot of interesting problems, and that's where you have to start thinking about, well, what's the problem I'm trying to solve? Because every company has a different problem. Right? So for this case study, we'll kind of structure the problem in a tractable way. We would like to try and understand the sentiments based on earning calls. So when earning calls happen, if you have tracked any of these earning calls, what may happen is like 4 o'clock, the results are announced, the stock goes up or down. It happened for Amazon, last week, I guess. The stock actually went up because they made their numbers for the quarter. But then when the earnings call happened, the stock actually went down because the major news was they're going to be making many investments this year in 2019, right? And that was a negative signal, and the stock actually dropped, right? So if you are trying to understand these sentiments, one way to think about it is, well, we'll have humans in the loop, and humans are going to be processing these bits and pieces of information and collect them. But if you look at it statistically, and I want to summarize information from the entire earnings call, many a times you don't want to look for earnings calls which had an average sentiment. You want to look for earnings calls wherein sentiment was very good or very bad, because that's where an opportunity could be. Right? So maybe you're interested in kind of summarizing some of these earnings calls to kind of understand the trends of how the sentiments has been increasing or decreasing over time. So those are all questions you can potentially ask, and data science is going to help you solve those kinds of problems. So here I have a sample earnings call. So this was from the Edgar database, which is SEC's repository wherein all the earnings calls have to be recorded and reported to the SEC. And it's available online, so you can go and scrape and download those data sets and work with it. A couple of companies are also basically taking this and summarizing it and providing it as data calls, data feeds. Now, some of the challenges we need to understand, and I'll explain why I have advanced questionnaires in this slide. One of the biggest challenges is interpreting emotions, right? So when you have earnings calls and analysts are expressing their views, how do you interpret those emotions? And the second thing is, these emotions are not always labeled, right? Because when we try to build a machine learning model, we want to have data sets which are labeled. So if I have a sentence which expresses extreme happiness, and then I have a tag which says happy, the next time I look at a sentence which has the happiness expressed in it, so I can say, okay, this is a positive sentence. So many a times we may not have those labels. So what do people do? They look for data sets which has labels in them, and then try and use those labeled data sets. And one of the data sets which is popularly used by data scientists and machine learning professionals is what's called as the IMDb data set. And this is a data set with movie dialogues. And each one of those movie dialogues have a sentiment, a positive or negative. So, you could potentially build out an algorithm leveraging a pre-labeled data set. Right? But, many conversations in the financial markets are not like as juicy as Hollywood transcripts, right? So it's not always easy to transfer knowledge you have gained in one domain and bring it into another domain. So that's the challenge. It's not easily fixed. So a lot of NLP, or natural language processing techniques, are being used to understand sentiments and summarize some of these statements. So I want to kind of give you a brief introduction to some of the techniques. So typically, when you talk about natural language processing, it's not just one solution. There are multiple applications, and we have seen them, in vogue through our Cortanas, our Siris, our Google Nows, or many of our devices. And that's basically having conversational agents. We are able to converse with some of these technologies. You can also think about topic summarization. So you have a whole topic and you want to summarize certain topics. Sentiment analysis, which I'll illustrate. Classification, trying to bucket each one of these documents into specific sectors or industries or specific topical areas. Keyword extraction. If you have a document with 100,000 words, which keywords are important? And if I want to search on those, how can I search on those? Tone analysis, kind of understanding the tone of the author. Machine translation, if I wanted to, if I'm watching a company in another country and the transcripts are in another language, can I automatically translate those and then make sense out of it? And then document comparison. So if I have two documents, are both those documents very similar? Are they dissimilar? So if I have an earnings call, over time, so can I look at each one of them? Are they very similar, or is the context changing, or is the tone changing? When you are kind of seeing different communications. So these are all interesting problems, and humans are extremely good at it. Given sufficient time and expertise and manpower, we can easily take each one of these problems and hire the right experts and solve those problems in an autonomous way. But with the volume of information which is out there, a lot of thought is being put into, can we automate some of these processes, right? So that's where we're going. Now, many financial companies are adopting NLP technology. So Bank of America launched a chatbot called Erica. Anybody using it? Tried using it? A couple of them. Does it answer questions? Correctly? Okay. And then JP Morgan put out a press release that their software does in seconds what lawyers would take many, many thousands of hours, about streamlining some of these document processes. So as you know, if computers can understand language, it can lead to many, many possibilities. And these are some of the things we could potentially do. And that's where many of our chatbots and other innovations are going. Now, traditionally, what used to happen was we were doing rule-based analysis. And that's where we were kind of figuring out, well, can I take a sentence, chop it into those words, and then kind of build out trees, looking at what kind of grammatical aspects are covered in this particular sentence. So that was what the original thought process of building algorithms were. But now, what's happening is, this is just kind of a snapshot of all the innovations which have happened in the context of natural language processing. There's been a curve, and people are moving from just syntactical assertions, which is think about bag of words kinds of concepts, to semantics, to thinking about pragmatics, which is like bag of narratives. So in order for a computer to understand what the text actually means, it has to kind of evolve in the context of how we process this information. Okay, and just to kind of give you an idea, language is hard to understand, right? So because it's very ambiguous, so we may have to qualify it with other words surrounding it so that we get a context of what that sentence actually means. Each word may have different connotations, and depending on the usage of the word in a particular context, we have different meanings to those words. Right? So this is just like Wikipedia entries of Jaguar. If you look for Jaguar, there's no one interpretation. Depending on the context, you can pull out different definitions. And then you can say the same thing. It's very hard to deal with because you can say the same thing in many, many ways. So you can't just take it like a structured problem statement and say, okay, if these are my parameters for x, this is going to be my y, because the way in which you can express x could be in multiple ways, multiple languages also. Okay. So the key idea here is, how do we process information, right? So you can potentially think about human insight, which is what analysts do. So if there's an earnings call, you know what? I don't have time to like sit on an earnings call. So let me wait for another day, and then my favorite analysts are going to summarize the call for me, and they'll also update their predictions on where the earnings are going to be for the next year or next quarter or whatever it is. And I'll just rely on my favorite analysts, right? So that's basically trusting experts, because I can't really process it. Let experts tell me what needs to be done. I could also have human insights. I could have my own analysts look at it and make interpretations of it. I could use APIs, and we'll talk a little bit about how we could potentially use APIs. This is where a lot of companies are trying to summarize certain information for you and providing alternative data feeds. Or the last one is basically building your own. You don't trust anybody else's solution. You have your own methodology, and we'll think about building out our own methodologies. Okay, so typically, if we wanted to do this from a data science perspective, and we want to build our own, this is what people typically do, right? So you need to have a way of ingesting the data, because the data, you're asking, where do we get the data from? So in this particular case, we are getting the data from Edgar, which is the database. And then we're going to pre-process the data set. In the context of pre-processing, we may have to think about, well, we have to let go of, white spaces or certain words which are nonsensical, graphical items in a particular document. So certain things which are absolutely useless for processing language. So certain things have to be taken out. And then we have to think about the biggest challenge, which is labeling. Right? Yes, you.
Can you say something about MapReduce, which was something that was, I think, is taken over by other functions in programs, and it basically mapped out what you needed and then did the reducing part of it.
Sure.
So can you tell me how that's, tell us how that's been incorporated into other programs like Spark or Kafka or whatever?
Sure. So the whole notion of MapReduce is, how do we split the task in such a way that we can give computational power to individual bits of data, and the analysis could be done on those particular nodes. For example, if I wanted to, basically count the number of words, which is the simplest problem in context of.
To get it into some kind of rectangle.
If let's say I wanted to, do keyword extraction in a document, and for keyword extraction, I'm just going to count the occurrences of each one of these words in my entire document, and then if I know the count of each one of these words, most likely the word which is most frequently occurring, eliminating some of the, like the words like and the and stuff like that. But if there are relevant words which always talks about oil, then maybe it has something to do with an oil stock or something related to energy industry, if you will, right? Or there could be some unique keywords which are kind of in the long tail, which may be of interest. Maybe there's a mention of a potential target company which could potentially be acquired. So we may be interested in this long tail of some unique keywords which was used, or some of the most frequently used keywords. Right? So that's kind of our business problem. So how do we go about doing it? So let's say there are 10,000 documents. So I can take one document at a time, count all the words, put together some kind of a data structure, and keep tally of all these words in the counts. Take the next document, take the next document, and keep on doing it sequentially. Right? What MapReduce does is, it just basically says, well, let's just parallelize this whole process. And instead of doing, let's say I have 10,000 nodes, right? So I can split this problem into 10,000 pieces and let each one of these nodes do this task of mapping the count of these words for those individual documents. And the reduce task is going to do the join of the results of all these 10,000 words into one entire outcome. Right? So what that will mean for you is instead of you having to do 10,000 iterations, let's say one iteration took 1 second, so you're wasting 10,000 seconds to get the whole job done. If I had abundant hardware, I could basically do the entire process in 1 second instead of waiting for 10,000 sequential seconds. Right?
So is this included, is this function included in Spark and Kafka and?
Well, in Spark, what it does for you is, you basically are relying on HDFS in some ways. So you can potentially look at it as parallel distributed computing system behind the scenes, and it does operations on it. So it has the language built onto it so that you can, look at this data which is already out there, and you can do operations on it, and you do operations on it as though you're doing it on a particular node, but behind the scenes it's going to distribute it, does all those operations behind the scenes, and brings the results back to you. Right? So it gives you that. That's why it's becoming more data friendly or data scientist friendly. And the initial approach for Hadoop was more programmer friendly because the programmer had to think about that abstraction of distribution. But now our data scientist is just thinking about the operations and the operational, putting it out on multiple nodes and all those engineering aspects of it's taken care of. Yeah. So that's an excellent question. So here, what we are trying to do is, so we are basically going to take a bunch of Edgar documents. We're going to be processing them. Now, the biggest challenge is labeling it, right? Because I do not know the sentiments of each one of these statements. So how are we going to, figure out the sentiments? Because the label is going to be whether it's positive or negative. So in order to do that, we can either recruit humans, ask them to read statements and say, this is positive, this is negative, kind of thing. What we will do is, we will basically contact 4 APIs. And the rationale here is, well, I will never be able to collect all the data and build out a labeler, which is going to be intelligent enough to process English in a good way. But for companies like Google or Amazon or IBM, they have a lot of data, and they have a lot of different algorithms. So they also have APIs which will give you scores based on the statements you're providing. Right? So what if we leverage these APIs to label these data sets? And then I'm going to build an ensemble model which will basically leverage all these scores. And that becomes my labeled data set. Right? So that's kind of a hypothesis I have, that instead of me doing the labeling, let me ask these APIs to do the labeling for me, and then I'm going to process it. Okay? And then finally, let's say, just to illustrate that you could potentially use multiple tools in this tool chain. You're doing a bunch of things in Python, and let's say your quant at the end is only doing stuff in MATLAB. So you may want to bring in MATLAB at that. Okay? So this could be a data science pipeline. So when people talk about data science pipelines, it's as simple as that. Just kind of structuring the entire recipe and then figuring out what stage everything is in what. Right? So a couple of things to note. So we'll have to think about the code. What code do we need to have in order to process all this information? The data question, like what data we're going to be processing. What do we need to do in the context of environment? What environment do we need? Do we need Python? Do we need MATLAB? Do we need Stata? Do we need Excel? Whatever that environment we're going to be using. And what's the recipe? What's the process of building out this entire pipeline? Right? And then we talked about the exploration piece. So I'll show you this in a practical case here. But the exploration piece would tell you, whether these APIs are actually working or not. Now, you may have to think about, well, obviously, if you are looking at MATLAB, then it has its own ID and it has its own language and syntax. So you have to think about how do you process all that information once you get it into multiple forms into MATLAB. And then you may have to think about comparing various APIs and then figuring out whether those APIs actually work in the context of sentences. So let me kind of show you the demo. That way you can get an idea of how this could be structured. So let me just. So what I did was we have a tool called as the Q sandbox. And each one of these stages, just for a second. So each one of these stages in the pipeline, so we have kind of structured this as a stage in the Q sandbox. So the first stage is the pre-processing or the scraping stage. So we are going to go into the Edgar database and scrape all this data set. The second stage is the processing or the pre-processing stage. The third stage is the sentiment analysis, wherein we are invoking various APIs and getting the sentiment scores. The fourth stage is the API comparison stage, wherein we are comparing each of these APIs and figuring out if the APIs actually give us the information we're looking for. And the fifth stage is the MATLAB stage, where we are actually doing the analysis. Okay. So when we have this pipeline in operation, this is what we're going to see. Let me just show you. The pipeline. So the first stage, this is just a practical application. When we do the full workshop, we're going to be building out some things, but I just wanted to give you a demo. So these are what I call as Jupyter notebooks. Most of you have used Jupyter notebooks. So this is basically how you can potentially build out different pipelines. So I'll show you a log. So this is basically the crawler log. So we had a crawler script. So it's basically going into the Edgar database and downloading all the data, and then putting it into a bucket called Amazon thing called as S3, where it's going and saving it in the Amazon repository. So I'm trying to see how I can minimize this. It's kind of annoying. Let's go back. So this crawler script we have, this is basically what's being invoked, and this is what people are going to write to scrape all the data. So obviously, this is not something a data science would be very much interested in. This is just a process which we want to go and figure out, like, how do we crawl this database and then put it into this Amazon S3 bucket. So Amazon's S3 bucket is storage on Amazon's cloud. So in case I wanted to share data with anyone or another part of my company, I can just put it into the S3 bucket and then download it from there. Okay, so that's like piece number one. So now it has basically told us that we have scraped the data. The second piece is the processing of the data. So what we're going to do is we will, so here we have pre-processed all this data set, and this is crawler looked at. And, so this is the pre-processing stage. So here in the pre-processing step, so we have written a Python script which will basically take all our data, chop all the data which we have gotten from the S3 buckets, and then we have a pre-process script so that we can look at the dates and other parameters, and we'll save the whole thing into a CSV file. Okay. So that was the second stage. I'm just kind of giving you a perspective that you have to design these applications in a modular way. Data scientist is not going to be writing this whole thing from scratch. Okay, so the data scientist is going to be like focusing on the things which they do best. Many of these things would have to be done in the context of data engineering. And the third stage is something you would be interested in, where you have gotten the data. Now you're interested in kind of processing and figuring out like what happens when I invoke different APIs. So this is the invocation for Amazon. So we basically sent this data to Amazon and asked for the sentiment. So here, so we got a bunch of sentiments from Amazon, and these were the sentiments from Azure. So they kind of give a score from 0 to 1. So most of the scores were between 0.3 and 0.7, kind of neutral. Some of these sentiments were negative and some of these were positive. And then, so this was from Google. So we basically looked at all the sentiments from Google, and then this was their graph. So somewhere close to 0 is neutral, but then this was the negative sentiments, so these were positive. Okay, so this was still processing. We just basically invoked a bunch of APIs and looked up like what it actually meant. Now we will connect and look at the summary. And this is what we see when we kind of look at all the individual files. So you can see that Google was red. So majority of the statements, the same statements, when you pass it to Google, Watson, the component API, which is Amazon's and Azure, there were very few statements which were classified as negative. And most of them, to comprehend most of the statements were considered as neutral. And then Watson classified most of the statements as positive statements. So this is kind of a summary measure for the sentiments, the same data when you pass it to different APIs, which means that every API for the same statement, some APIs could term the statement as positive, some could term the same statement as neutral, some could term the same statement as negative. It's not a proven science yet, right? Now, just kind of a summary measure. Now, if you look at some of the positive and the negative statements, so if you look at like the most positive statements, so you can see that in addition to being highly strategic, Covidian acquisition is also extremely attractive financially with achievable cost synergies are expected to make transaction accretive in the first year on a cash basis and within 2 years on a GAAP basis. The combined company will also generate significant free cash flow, which can be deployed with much greater flexibility. So this was like the most positive statement Google found. And the other APIs also found this statement to be very positive. So think of a dashboard wherein the analyst, instead of just looking at a whole entire statements, these most positive and most negative statements are actually highlighted for them so that their eyes can go directly onto those segments in the earnings call rather than they having to skim through the whole thing. And the most negative statement was the gross margin continues to include significant spending on additional resources, mostly diverted from R&D to address quality issues in neuromodulation and diabetes, which negatively affected the Q1 gross margin by approximately 40 basis points. So without any human involvement, we were able to just basically take this entire statement and classify ones which were positive and then some of them being negative. Right? So we've been able to successfully label these. Okay, so some other positive and negative statements. So the point here being, we actually have now the ability to basically just send out automated scripts into the cloud. It's going to go and pull the data from Edgar, pass it to the API, and we are able to filter it into specific segments which are most positive or most negative. And then we can do additional analysis. So the last piece I wanted to just illustrate for you was, so in case you now have a data set with statements and which were statements which are positive or negative. So I could potentially now invoke another tool like MATLAB maybe, and then kind of run my own analysis. So the illustration I have for you here is, it involves thinking in multiple contexts. Excuse me, we'll do that later. So, so in the context of replicability, this is a completely repeatable process. So we can kind of iterate through the whole thing stage by stage. And I will share a link to the presentation and the experiment and some of the summaries which you have seen till now, so that you can kind of digest that at leisure. Okay. So One of the key things to understand in the context of data science when we're looking at these 10 steps, just make sure that you are kind of defining the problem on what you're trying to do beforehand, because many a times you kind of just go through the whole process and we don't really see why we are doing what we are doing. Right? So in this particular problem, we wanted to get the sentiment scores for an Edgar data set, and we just put together this pipeline. Okay. So I will stop here. So it's 10:30. We'll take a quick break. Any questions regarding the case study or any of the approaches? Yes, please.
What does that mind glyph represent?
This.
The blue and yellow thing. What's that?
This is basically the logo for Python.
Python. Oh,
okay.
Thank you.
So this is the Python logo. This is the MATLAB logo, and this is the Python logo.
Ah.
Please.
So I was wondering, what are some other commonly used pipeline procedures you just showed besides the QuantUniversity ones?
Yeah. So there are every cloud vendor has their own pipelining tool. As you know, all cloud vendors are moving from infrastructure as service to platform as service to software as service. So some of the software vendors, Amazon, they have like software as a service where you can just go and use the software as is. But they're also providing like data pre-processing tools and Lambda functions, and you could potentially daisy chain all those things and put together various pipelines. Watson has a Watson tool to put together a whole pipeline. Microsoft also has a machine learning, I think they call it the Studio, wherein you can basically take each one of them as widgets and then use those widgets to kind of say, okay, this is where I'm doing my data acquisition, this is what I'm doing. Yeah, there are some companies which are specializing on pipelines and defining those pipelines. Yes, you.
What's the latest on Google's tensor processing units?
What's the latest?
Yeah, is there anything new on that? And is it a threat to NVIDIA?
I think they play with each other well, but I think the TP, Google Cloud now supports NVIDIA's, I think, the latest processors. So that was like the latest announcement. So I think they're like two different things altogether. With one,
Google has obviously must have TPUs in their cloud.
Google does have some of those. I don't know specifically whether how they play with the NVIDIA stuff, whether it's like a complementary service or it's like two parallel things where we can choose the NVIDIA stuff versus the TPU stuff. I don't know that particularly. Yeah.
So when you do the Jupyter notebook, and then what you said was the setup part was done by data engineer.
Yeah.
And then the latter part was done by data scientists.
Data scientists, that's right.
Like how they communicate, and what's the duty of the data engineer?
Right. So typically, the role is kind of you can look at the role in two ways. One is everybody was called a data scientist before, but when you went and you figured out like most of the stuff was actually data engineering, not really data science. Right? And then people started figuring out like, okay, this is a role of a data engineer, this is a role of a data scientist. So the data engineer's role typically is in the context of scraping, acquiring the data, missing value analysis, understanding where the data comes in what format should the data be in for final processing. The data scientist role is more algorithm selection, algorithm tuning, figuring out which particular algorithm works best for the business case at hand, and how do you actually do the deployment and stuff like that. So, and now this whole role of DevOps or development operations is kind of coming in. We are thinking about containerizing it, replicable containers, and how do you kind of build out things which can potentially be replicated in the process. So that's constantly evolving. So the data engineer, in the past, data engineers were typically thought about as people like database professionals who are just structuring the data and making it available. The role is kind of increasing in complexity because of the nature of data. It's no longer just structured data. You got to think about text data, if you will. And then you have to work with the data scientists to figure out like what aspects of it should be processed and how do we actually make it available. So there's a lot of interaction between those two teams. Okay, yes, Anish.
So, predominantly ensemble model from the different sentences.
Right.
How do you go about doing that? Because you now it's
We just
unlabeled,
used a
right?
weighted average, a simplistic weighted average, because we did not know. You could, we looked at a couple of things. For the same statement, if we looked at majority voting.
Yeah.
So if there are 4 API scores, first of all, we normalized all of them. Some of them are from 0 to 1, -1 to 1 kind of a thing. So we normalized it. And then we looked at majority voting. And if there were evens, we used something for breaking the tie, random tie break kind of a thing. But then we decided just to do like a weighted average, because we just wanted to, we were looking at some of them, and in some APIs, majority were just classified as neutral. And in those cases, you're not gaining much insight, so you can potentially just ignore that particular data set altogether. So we weight that particular data source lower compared to the other ones, which were able to discern the sentiments in a much broader scale. This is my question. Yes, please.
So let's say you've built a program that's going to do the sentiment analysis. You're able to get the feed off of Edgar for free. What's the cost to access the 4 different APIs?
Yeah, so each one of them has a different, but it's minuscule. A couple of cents for 10,000 messages kind of a thing. So the cost is going to be extremely low, because this is per 1,000 API calls kind of thing. So each one of them has their own chart on how do you actually process, but it's minuscule. Any other questions? Okay, so let's take a quick break. We're running a little bit behind, so we will regroup at 11:05 for the next session. Okay, thank you.